Miller from BP. And at this point, I would like to take the opportunity to thank Dr. Miller for getting us a large sponsorship from BP. I would also like to thank all of our sponsors, main sponsors and co-sponsors for contributing so generously to this ICDS conference. Our very first talk of 3 talks, this first part of the afternoon session, will be presented by Dr. Schulz from Michigan Technological Institute. And if you just go on. Do you want the I guess.
Good afternoon. I want to change a couple things before we get the talk started. The title given in the program, we've made quite a bit of progress in the last 6 or 7 months, and so we're expanding the scope of our presentation a little bit to describe more of the work that we've done with SO2 and Syria, zirconium, and oxides. Since we submitted the abstract to Alan Nelson, who is a PhD student on this project, graduated, took a faculty position at the University of Alberta, and I've since moved to the J.C. Schwalm School of Chemical Engineering in Mississippi State. I must say, too, that this is the first conference I've ever been to that Wild Turkey has been one of the sponsors. As such, I certainly want to be part of it. Just very quickly, a little bit of a roadmap of where we're going. I'm going to provide some introduction to you that may be repetitive for those of you familiar with automotive catalytic converters, but I'll give you just a brief overview of where things sit and some of the challenges ahead. I want to talk about our approach to modeling these emissions control catalysts using fairly classical surface science techniques, and then talk about the first 2 phases of the study and an ongoing project, and then try to summarize kind of where we are and speculate just a bit on some of the sulfur species that may be existing on these particular materials. Well, the concept and use of catalytic converters has been around quite a while. Most of us are familiar with the general concept where we take air into, for the most part, a gasoline internal combustion engine. We react it with fuel, and then we exhaust the reactant gases out and run it through essentially a packed reactor or catalytic converter. And from this catalytic converter, then what we do is we take essentially things that are non-regulated, that are we don't want here, and react them here into something that's regulated in the amounts that satisfy us. And if you look historically over time, the composition of what's allowed to come out has been changing rather rapidly. Well, it turns out that, like any technology, there are constantly changes and challenges to this, and there's some increasing demands that are being placed on catalytic converters today, and I've listed a few of them here. For one thing, we like lifetimes in excess of 100,000 miles, regardless of where you drive. So if you're pulling a trailer up the mountains in Wyoming, if you're driving in New York City, you'd like to make one sort of catalytic converter that will work regardless of driving conditions. The second major thing is we need increased thermal stabilities of these particular catalytic converters, and I list 1100 degrees C here. I was in a talk about a week ago where somebody said up to 1400 degrees C, which we maintain the catalytic performance. Now, why do you want to do this? Well, we want to move the catalytic converter closer to the engine, close to a couple of catalytic converters, so that we can get light off under cold start conditions and much earlier. We need to possess a high oxygen storage capacity, or maintain it would be a better way to put it. And then we have to have a high resistance to things like sulfur dioxide, phosphorus, and so forth, present in fuels which tend to deactivate our catalytic materials. So these are some of the things that we have to keep in mind as we look at these materials and how they react chemically. So what is the role of sulfur? The U.S. EPA has identified fuel sulfur as a problem. Additionally, as we would surmise, the more sulfur that's in the fuel, the more SO2 produced, and the worse problem it is activates the catalyst over time. So this was some of the reasons that we chose to start doing some fundamental studies of SO2 absorption on these materials. Well, looking at the system that we have to deal with a little more in depth, here's your catalytic converter here. We take a cross section, open it up, we have the catalyst block, monolith block in here. And if we look at a piece of the monolith that's shown over here, where this inside kind of brown part is a ceramic monolith, and then there's a wash coat on the outside, which contains alumina, Syria, zirconia, typically at least one metal, which could include palladium, platinum, and rhodium. So we've got this complex mixture kind of operating synergistically that makes this a bit difficult to model and study fundamentals of how sulfur interacts with these particular materials. What further complicates this is most of you have seen these sorts of diagrams where this is conversion on this axis, simulated air-to-fuel ratio on this axis. We like to operate right around the stoichiometric ratio, where we see nearly complete conversion of hydrocarbons, CO, and nitrogen oxides. Well, the problem is that in an engine, we've got periods of fuel excess and fuel lean, or oxygen lean and oxygen excess, depending on how you want to look at it. So we need to be able to operate our catalytic converter in a range around this particular time, and this is where the concept of oxygen storage capacity comes in. Now, this is a cartoon here, which is just meant to show you in general what's occurring. We have a oxidation reduction system, which helps us work here. Under fuel lean combustion conditions, or oxygen rich, we see a change in oxidation state from Cerium plus 3 to Cerium plus 4. In essence, we store oxygen in the lattice of the material under these conditions. Well, when we have fuel rich or oxygen lean, we see a change in the Cerium oxidation state from the plus 4 to the plus 3. We release oxygen, and this way we can have a source of oxygen regardless of the environment that takes place. So as we look at these particular materials, we have to have cerium oxide around essentially to allow us to be able to do this plus 3 to plus 4, plus 4 to plus 3 change in oxidation state, so that we have a constant and plentiful supply of oxygen. So what have we got? Well, if you're looking to model this, when I say model, I mean from an experimental point of view, we have a complex synergistic system. We have typically 3 metal oxides. We have a quarterite support, cerium and zirconium oxide promoters, and then a metal active phase, which can contain palladium, platinum, rhodium, a mixture of different things. Our reaction environment, we can go up to 1,000 degrees K, which may not be that high temperature, but we have multiple components in the exhaust. So when you put all these together and you want to look at fundamentals, it becomes difficult. We can't really take all these components and put them all in there at one time and hope that we can really address any sort of fundamentals. So we've got to simplify this down somewhat while retaining some aspects of reality. We also need to simplify it enough that we can use things like XPS, Auger spectroscopy, and so forth to make some determinations of what may be happening. Well, we had a couple options of what we could do. Okay, my background really strongly in single crystal oxides, and that's of course what we'd like to do. Look at these. You can look at cerium zirconium or cerium oxide. Zirconium oxide has been quite a bit of work done on cerium oxide single crystals. We'll talk about that later. Some advantages: a very defined surface structure. The problem is really the presence of the multiple oxides here is absolutely critical. And so studying this on a
surface structure is in these particular things in the same way that you might in a single crystal material. So our approach was to develop and characterize these mixed metal oxides first. Secondly, we had to construct a small microreactor hooked up to UHV. This has been done by many groups. This is not terribly unique, but that was the second thing we had to do. And then once we had those done, then we wanted to look at the metal oxides, cerium, zirconia as a function of composition, and how sulfur interacted with these in the form of SO2. And eventually we want to put palladium on top of these and look, and that's part of what one of my graduate students is doing right now. So the first part, characterization of the model materials. Just a quick slide on the preparation. We used cerium ammonium hydroxide, zirconium oxynitrate, went through a synthesis procedure similar to that used by Simon Hingsprue at Wayne State University, and we formed these oxides of various compositions. Then we go through a series of steps here. We changed these around quite a bit, tried different things, and did some electron microscopy work to make sure that we were getting wafers that had a minimum topographic, essentially as smooth as possible on a EM scale. And so then what we get are these discs that look about like this. Over here they're about thumbnail size, and they're fairly robust, so you can put them in bags and move them around if you have to without them breaking up. And this is what we use for our particular studies. Well, the first thing that we had to do with the oxides was take a quick look at their microstructure using X-ray diffraction. What's shown here are just a series of XRD scans starting at 100 atomic percent Syria, and going to 100% zirconia. And we would expect a cubic structure for all compositions of Syria until we get very close to 100% zirconia. And here what we see is a monoclinic structure. The lines on here correspond to the cubic structure. It turns out if you put the lines on for a monoclinic structure, it would exactly line up here. So we in essence got what we thought we were going to get from the XRD, and we were pleased with the crystalline structure of our samples. The second thing that we wanted to check for was, are we seeing a surface composition that's representative of the bulk? And so the assumption we made here is that if our surface composition is representative of the bulk, we should be able to look at example of zirconia signal measured by Auger or XPS, and it should be directly proportional to the bulk composition. So if we plot the intensity of that signal versus composition, it should be a straight line if we're seeing essentially the same composition of the surface of the bulk. And here is it shown for Auger, and we use the zirconia here for both the XPS and Auger. We see a nice straight line, goes right through. You can ask, why didn't you use Syria? If any of you are familiar with the XPS of Syria, it's a mess. And so zirconia is very clean, and so this made a lot more sense to do. So we were satisfied as much as possible that we were getting our surface composition as representative of the bulk of the material. We also took a look at seeing if there was any changes in oxidation state as a function of composition or preparation conditions. And we see some small shifts in the binding energies. However, none of the shifts are significant enough where we're seeing a complete change in oxidation state. If you're familiar, especially with cerium, it is always partially reduced. In other words, you always have some vacancies and things at the surface. It's very difficult to fully oxidize. By comparison with some of the single crystal work, we estimate our cerium here is what would be termed a nearly oxidized surface. So we've got it's not reduced cerium oxide, and our binding energies tend to support this. Now, what was more important was we wanted to get a feeling for the amount of oxygen that might be available at the surface for bonding. And I'm going to apologize for this kind of ugly plot that I'm about to show, but I think it illustrates just a couple things. Okay, there's clearly a lot of scatter here, but in general, what we see is we see two ranges. We get a ratio of about 2.6 to 2.7, and then when we get to 30% atomic percent zirconium, we see it step down just about here. We're working right now on replicating these again so that we see if we can't tighten this up. But the important thing is that we see under some range of compositions more oxygen available at the surface surface for bonding than we do down here. And this is going to be increasingly important as we go through the talk, look at temperature program absorption results and so on, as well as speculate some on some binding with the SO2 to the surface. So what can we say about our model catalysts? Well, we did some surface oxygen, reducible surface oxygen calculations that I'm not going to show that basically support the general idea that at 30% Syria or less, we tend to see these, or higher, excuse me, we tend to see quite more surface oxygen. As the amount of zirconium increases, we see less and less surface oxygen. The binding energy shifts are consistent with a shift towards a lower cerium oxidation state, but it's almost a 2 to 2.5 eV shift from one oxidation state to the next. So the 0.5 eV shift that we see is relatively small, but we think it's due to maybe some vacancy formation. And I didn't show VET and some other measurements here, but they're consistent with what's expected for these type of materials in a catalytic converter in a car. So in general, we felt that, okay, this is not a perfect model, but at least we've checked as many things as we can and believe that this is a reasonable representation of at least the promoters in the system. So what we wanted to do next then was look at sulfur absorption on these particular materials. Being a good surface scientist, the first thing you think of doing is temperature program absorption. And that's what's shown here. For those of you who may not be completely familiar with this experiment, what we essentially do is we take our samples in ultra-high vacuum, we cool them down to 100 degrees Kelvin, we expose them to SO2 enough to get a saturation coverage, then we pump out the vacuum system while maintaining it at 100K, then heat it up with a mass spectrometer in front of it from 100K to 1000K and see what comes off. And that's what's shown here. Temperature is on the x-axis. This particular top part is for 100% cerium. This is for a mixed oxide. This is for 100% zirconium. And we see some interesting things. A couple things I'd like to point out. In general, the only thing we saw coming off was SO2. Okay, we did not see any evidence for SO3. We're not able to detect an O2 desorption signal. And so what's shown here are the massive charge ratios that we would expect for SO2. It is cracking fragments, and then the one on the bottom here is for oxygen, and you can see that in essence those are flat. When you squint for a water main, pretend you saw something there, but in general these are flat. Now what we do see is one chemisorb desorption state for Syria. We see two chemisorb desorption states for the mixed oxide, and then for zirconium we see one primary one, and you can call this a second one or a shoulder that's over here on this particular side. So TPD gives you a little bit of a hint about things. So this tells us we think that we're seeing a single type of desorption state for SO2 on Syria, two different ones for SO2 on the mixed oxides, and then one with some sort of energetic difference on the zirconia, and we'll come back to this later. Now the problem is that this is an ultra-high vacuum, so if you talk about a realistic model, we're 10 to the minus 10 torr, which is orders of magnitude away from anything you would see in a car. So what we decided to do then was we needed to expose the sample to SO2 under more realistic types of conditions. And so we built this microreactor, and the only important thing I'd like to point out is we had a mass spectrometer hooked up to it. All the experiments we did were in a batch mode. We would like to do it in a continuous mode next, and that's one of the things we're going to pressure. And we try to pick these numbers as reflective of the highest sulfur content fuel, maybe real garbage fuel, but in general, that's the higher one and then a lower one. Each of these temperatures was a fresh sample. So we essentially did the OJ characterization, did the exposure to SO2, did the OJ spectroscopy, and then started over with another sample. So each of these temperatures represent an individual experiment. So in my time, it was a week. In graduate student time, it was like a year. Okay. So sulfation of the Syria only, this is what we started with. What's shown here are some OJ results. This is the 100% Syria. This is the this is the clean sample. This is the lower pressure exposure. This is the higher pressure exposure. And what's shown here is I just was illustrating where the sulfur tends to grow in. If life were easy, everybody would do these things. The problem is zirconia transitions occur directly over the top of sulfur. So when we show the results that we got with the mixed metal oxides, it took a lot of numerical jockeying to be able to extract those signals out. But anyway, with 100% Syria, what do we see? Well, we look at these different temperatures, and this is just simply the integrated area of our OJ transition. And the first one we see is at higher pressures here, which we think corresponds to essentially a monolayer of coverage. We do not see a difference in coverage as a function of temperature. Now, we'd like to point out this has nothing about the state of surface species on there. We're pretty sure that we see some changes, sulfate, sulfite, and different things as a function of temperature, but we're still investigating that. For the lower pressure, we think this corresponds to about 0.15 to 0.2 of a monolayer, and some of what we're seeing in this variation we're sure is pretty due to the fact that no matter how careful you are in a pressed powder, you're going to have voids in places where SO2 can react and absorb. And so these, if you look at these, there's no necessary trend to these, but you do see some variation. But in general, what we find is we didn't see big differences in just the raw amount of sulfur as a function of temperature, but we certainly did as a function of coverage as reflected by these different pressure measurements. Okay, for the mixed oxides, we plotted them as follows. And what this represents is this is atomic percent zirconium from 0 to 100%. This is the ratio of the zirconium to sulfur peak that we extracted from our data, and this is for the low coverages, so probably a tenth or so of a monolayer. And what we see is it's not what we expected to see. Okay, we see a little bit go down, then we see this maximum out here at we'll say 80% zirconium or so. We believe that this is due to the fact that we're seeing additional oxygen vacancies at this particular set of experimental conditions, and so that if SO2 goes down, the first thing it looks for is a vacancy at very low coverages. This is not that hard to believe. Okay. Then the question is, well, if I get my surface coverage a lot higher, what does it look like? And that's what's shown here. Okay, the same sort of axes, and now again the zirconium to sulfur signal. And what we see here is more what we thought we might see. Okay, at higher pressures, what we see then is much more sulfur going down at high Syria concentrations, and then it decreases. Now, just to put this in perspective, and we can try plotting this many ways, but that peak that you saw before out here, okay, if we plotted that data on the same one, would go and just come right to here. So this represents probably on the order of 5 to 10 times as much sulfur is going down is under the low coverage conditions. So the question now is, okay, we see some differences in the way sulfur goes down on these materials as a function of both composition and coverage. So how is SO2 going down? Well, an absorption model where SO2 only absorbs at oxygen vacancies is not consistent with our results that we saw at different coverages. Steve Overberry's group has looked at Syria 1,1 single crystal surfaces, and they found reduced Syria, SO2 absorbs at the Syria +3 sites or vacancies, and on non-reduced Syria, the principal absorption site is on surface oxygen anions. Okay, as I mentioned earlier in the beginning, our particular material, even though it's polycrystalline, is much more like what they term their oxidized cerium surface, and so it's likely that SO2 is going down as some sort of species that has one sulfur-oxygen double bond and then 3 oxygen single bonds that would be bound to the Syria. And we think that this could be occurring at these places where you have these oxygen vacancies. And so that the oxygen group comes down, and then you have some sort of magical bonding configuration that happens. Like I mentioned before, this has been observed in IR. This sort of thing has also been observed in IR. The XPS results are confusing to say the least because it involves lots of peak fitting, and you can probably kind of make it whatever you want depending on how you fit your peaks. However, we are looking at both of these particular species right now in follow-up XPS experiments that I hope will eventually give us a better model for what is occurring. So, the differences in sulfur absorption in our experiments are really thought to be differences in surface sulfur coverage. One of the things that we can clearly say is the way SO2 goes down is related both to composition, which we think is then related to the amount of oxygen at the surface and the number of vacancies that are at the surface. Temperature did not have a significant effect on the sulfur absorption and the conditions for our study, but again, we're looking at this to see if we can't track exactly how the species are developing as a function of temperature, and we believe that we're going to see, get some more insight into this particular phenomena by looking at those experiments. And let me just very quickly acknowledge the Forward Motor Company University Research Program. In Michigan Tech, we had a DOE program for automotive technology. The 2 graduate students who worked on that, National Science Foundation, and I have 2 students at Mississippi State that are currently working on this as well. And I'd be happy to answer your questions.
You show the ratio of oxygen to the sodium and siliconia is larger than 2, but you see this is maybe some oxygen vacancies is formed. But generally, if the ratio is larger than 2, this is oxygen-rich condition. Maybe if it's less than 2, maybe it's oxygen deficiency, or some oxygen vacancies can be formed. But you show that it's larger than 2. Still see some oxygen vacancies formed.
So you're referring to the
data from Osher analysis.
Okay. From OJ or XPS?
Yeah.
XPS?
XPS.
Yeah. Yes?
Figure. Oxygen varying with the ZrO2 Syria.
I will talk to you about that.